This diagram illustrates the population distribution of bad dreams across a large demographic sample. Notice the peak right in the middle. Dysphoric dreams are a nearly universal human experience, occurring at high frequencies even in perfectly healthy individuals. Evolutionary psychiatry interprets many highly aversive states, prompt an organism to avoid danger, conserve resources, or respond adaptively to loss. Applied to our sleep cycle, this logic suggests negative dreaming serves a specific biological function. By acting as a virtual environment for threat simulation, the sleeping brain can safely rehearse evasive actions and defensive responses against potential hazards. Generating these internally varied simulations prevents a cognitive phenomenon known as overfitting. If our minds were exclusively tuned to our safe, mundane daily routines, we would be incapable of flexible responses when unexpected dangers actually appear. Because bad dreams participate in this necessary threat-sensitive processing, the mere presence of terrifying imagery does not indicate clinical dysfunction. A highly aversive dream is often the expected cost of healthy emotional work. The standard clinical response to disturbing dreams has historically focused on the narrative itself, attempting to diagnose and treat the specific monsters, failures, or hazards the patient visualizes. Nightmare research is now shifting away from interpreting dream content. The focus is instead on network pathology, tracking how the underlying neural and psychological systems behave before, during, and after the dream. The key metric in this approach is cross-night coupling. This measures the exact degree to which one night's sleep alters daytime functioning and how that altered daytime state impacts the next night's sleep. This diagram represents a healthy neural response. A nightmare pulses as an isolated warning, fading to baseline before the day begins. But in a pathological state, nocturnal distress links to daytime anxiety, creating a dense, cyclical feedback loop that continuously feeds itself. A distressing dream becomes a medical disorder only when it crosses this dynamical threshold. The transition from a self-limiting biological output to a maladaptive cycle dictates the pathology, not the content of the dream itself. To map this transition, we plot distress levels. In a stable regime, a bad dream acts as a transient perturbation, a sharp spike at night T. Upon waking, the distress dissipates, dropping to a stable 0 throughout the following day. Because daytime arousal has zeroed out, the patient approaches their next rest period without elevated vigilance. The sleep architecture for the following night remains perfectly intact. This second graph illustrates the destabilized regime. A nightmare causes a sharp spike at night T, but the dissipation fails. Psychological distress bleeds into waking consciousness, remaining elevated and unsettled throughout the entire next day. This sustained distress elevates physical autonomic arousal. A secondary line tracking heart rate and cortisol directly mirrors the erratic pattern of the psychological state. These elevated lines converge before the next sleep cycle, generating a spike in bedtime apprehension. This pre-sleep dread forces threat simulation, ensuring the nightmare on night T+1 is even larger. The initial dream is not the driver of the pathology. The disorder originates in daytime carryover and the resulting fear of sleep corrupting the subsequent night.
Computational psychiatry uses a specific mathematical concept to measure this escalating cycle, loop gain. This equation models the system's volatility. The first half measures how the distress of night T mathematically elevates daytime vigilance. The second half measures how that vigilance directly converts into pre-sleep apprehension. The final equation block connects back to the start. This pre-sleep fear radically increases both the probability and intensity of a recurring nightmare on night T+1. This mathematical cycle compounds across days. Uninterrupted, the loop drives chronic insomnia, severe emotional dysregulation, and major impairments in daily functioning. Effectively treating severe nightmares requires lowering this computational loop gain.
Clinical hours interpreting surreal dream elements do nothing to break the mathematical propagation of distress. To accurately diagnose a high-coupling nightmare disorder, clinicians rely on a 5-variable threshold model. This matrix maps a patient's transition from a stable, self-limiting pattern into a destabilized regime. The first variable is recurrence. Occasional bad dreams appear intermittently and do not predict later episodes. In a threshold crossing pattern, one episode reliably increases the likelihood of future episodes. The second is physiological activation. A normal bad dream produces mild, short-lived emotional discomfort. A pathological nightmare triggers abrupt awakenings accompanied by severe autonomic spikes, such as tachycardia. The third variable is next-day carryover. Daytime hypervigilance indicates the threat simulation system is failing to disengage upon waking. The fourth variable is functional impairment. The disorder becomes clinically relevant when sleep avoidance and chronic fatigue actively degrade the patient's waking life. The most critical and complex indicator is the fifth variable, thematic rigidity. A healthy threat simulation system constantly explores new narratives, varied scenarios, and different defensive actions. This internal variability broadens learning and builds cognitive flexibility. In trauma-linked nightmares, this flexibility collapses entirely. The system begins to rigidly, identically replicate the specific traumatic event, looping the exact same visual and emotional sequence without variation. This rigid replication represents a total failure of the brain's evolutionary fear extinction mechanism. The dream ceases to function as an exploratory space, degrading into a destabilizing replay mechanism. When these 5 variables align, particularly the presence of thematic rigidity, the patient is no longer experiencing a healthy bad dream. They are trapped in a severe PTSD-linked pathology that requires immediate intervention. Modern clinical interventions utilize a process called dream engineering. The objective here is never to medically enforce continuous, positive, happy dreams upon the sleeping mind. The true objective is to selectively hack the sleep cycle to sever the rigid feedback loop. By breaking the connection between nocturnal distress and next-day apprehension, clinicians can restore cognitive flexibility to the system. The primary intervention for this is imagery rehearsal therapy, or IRT. IRT specifically counteracts thematic rigidity. Patients are instructed to re-script their recurring dream during waking hours, altering the narrative, the emotional tone, and the action possibilities. This conscious rehearsal restores their narrative agency. A technological enhancer called targeted memory reactivation, or TMR, can accelerate this therapy. TMR uses highly specific sensory cues, such as a distinct sound, delivered during specific sleep stages. This external stimulation triggers and reinforces the rescripted IRT narrative while the patient remains unconscious. These interventions do not succeed by erasing fear from the brain. They succeed by physically breaking the bridge between nocturnal distress and daytime apprehension, lowering the overall loop gain. Dream engineering operates under strict physiological constraints. If TMR auditory cues are delivered at the wrong time or at an improper intensity, they can fragment the patient's delicate sleep architecture. There is also a severe risk of cue contamination. A mistimed signal might accidentally trigger a micro-awakening. If this happens repeatedly, the cue becomes permanently associated with threat arousal instead of the intended corrective safety signal. Due to these destabilization risks, the blanket medicalization of bad dreams or the use of routine dream optimization consumer technology is inherently dangerous. The clinician's responsibility is strictly to evaluate system stability and monitor loop gain. It is not their job to police the specific narrative content of a patient's sleeping mind. A mature science of dreams recognizes terrifying nightmares as a vital, functional element of our deep evolutionary design. Intervention is required only when the system loses its flexibility and traps itself in a loop.